So we are going to continue from the where error lives, but I'm going to give you more examples and show how things go visually. So I'm not going to repeat the slides, but show you some information about how context switch occurs, etc. So actually, I told about this just 2 hours ago, but I'm just repeating. I'm going to try to be more efficient this time, but please stop me if you have any trouble following. So I'm going to just give you a brief summary of what you have learned last week. You actually learn about a usual flow of a program which has this function calls and some loops here, and there are some jumps. There are non-local jumps as well. So these are this programming language stuff, and in an operating system this story is not that easy. We have process 1 and process 2. So this is a strange visualization of function calls, nested function calls. Sorry about how strange it looks. But the thing is, in a usual flow, as a programmer, without having anything in operating system in your mind, there are loops. The program can jump into itself, go to some area within the program, and so on. But in the operating system, since we share CPU, at some point of time, we can have operating system intervenes and CPU wakes up here in P2. So CPU is intervened and it is going to wake up in this other stage. Okay, and this is what we call a context switch. And in order to make an operating system actually running and useful, it has to do this. If you remember, the time sharing system means the process, the CPU is switched among the different processes, different entities. And this happens a lot in a working system. Actually, I prepared you one demo of that, so let me just show you. Okay. So you are going this. So let me just, I'm not sure how it looks when I maximize the window, but the idea is, this is the timeline. It says just 10 seconds, not more. And these are the processes in the system. So let me just zoom some area so you can read it better. And so, for example, here, during this time, CPU is switched from teams to timer, then to swapper. So this is the kernel process actually. Then the web content, then Chrome, this one. So CPU switch like that. Since it is a multi-core system, you may observe some overlaps because there are multiple CPUs, but the idea is in 10 seconds, this happens. So there are many context switches in a working system. I prepared you a more brief version of that, which I have only 4 processes. The others are the system processes. And let me talk about the characteristics. The P1 and 2 P1 instances, 2 different processes executing the same code, P1, are number crunchers trying to crack a password, something like that, some silly code. P2 is doing some number crunching, but between them, there are 1 second sleep. So this is a sleep area. This is another sleep area. This is another sleep area, like that. So if I, for example, zoom this area, you will see the CPU. This is, by the way, a virtual machine having only one CPU, so I can observe the things better. So the idea is, during the sleep periods like that, CPU is switching between P1s. And when P2s wake up, the CPU is shared between P1s and P2s. So it is divided into 4. And it goes like that. You will see this pattern in such a system. So that means we need a mechanism intervening this operation. So the operating system cutting this operation in half at this moment, giving CPU to worker, and from worker P1, from P1 to another P1, and it goes like that. And this mechanism is implemented by the operating system, and this is what we call a context switch. So the whole purpose of an operating system is to get that service to the CPU, service to the processes, so they can use the CPU. Does the swapper zero include idle time as well, or is that all meaningful work by the kernel? I'm not sure what it does, but zero means it has no process ID, so probably it has kernel housekeeping task. It may be idle, because in that graphic it was desktop, so my desktop was sleeping some of the time because it's totally interactive and there is no number cruncher. In the later figure, there are 2 number crunchers always active and 2 others active after sleeping. That means there is no need to be sleeping. So probably it is the idle task and kernel's idle task. But it's a good question, by the way. So the this context switch operation, you're seeing the whiteboards, do you? I lost track of what you are seeing. Okay. So this context switch is handled through a mechanism that we call the timer interrupt. Actually, we have studied that last week. And actually, there are 4 points of an operating system intervening this operation. The purpose of operating system: let processes use the CPU. When I was an undergraduate student, I had this idea of having operating system as a service, reading next instruction, executing, reading next instruction, executing. But this is not true. This was wrong. The correct interpretation is this: CPU belongs to the process. Process executes any instruction it likes in this restricted mode. And once in a while, operating system intervenes this operation, cut, and let other process execute. So it takes CPU from one process to the other and does the context switching. And most of the time, in a good operating system, most of the time, the user processes are executing. Okay. So the first mechanism of this unusual flow, exceptional flow, is context switch. So P1 leaves CPU, P2 takes it. So in order to implement that, we need to have this exceptional flow. The second mechanism is hardware interrupts. The hardware interrupts are handled through hardware. So we have inside of CPU. Sometimes it is externally. There is an interrupt controller. So this hardware devices, when they trigger an interrupt, CPU will execute an interrupt service routine. So this is basic computer organization information. The idea is when data is ready, like for example, this is a network interface card and there is a network packet, it doesn't wait. It doesn't wait for your number crunching application to finish and leave the CPU. It has to be handled as soon as possible because there's a urgent traffic, and it might be much more important, like user controls, pressing Ctrl+C and so on. So we cannot wait for process 1 to finish. What we need to do is we need to cut process 1, do this hardware thing, and leave CPU to process 1 again. So process 1 is going to happily execute. At some point, there will be an interrupt. So we will have CPU enforce some ISR call. It is going to handle I/O. And then it calls RET-I, return from interrupt. So P1 can execute again. So during execution of a process, you will see a lot of those. Okay, there are many interrupts during execution of a call. Can I show you that? I believe I can. So this is my virtual machine, and this is what's happening. So let me just. So this is like 5-6 seconds of execution in my machine, and this one is basically having this many interrupts during this processing. It is a very simple process. There are some I/O operations, ATA, PII, XR I/O operations. S3 is the network card. There are some network card operations. I8040T is I think something like console events. I press keyboard and so on. So when my process is doing nothing, actually I didn't do much of a thing during this IRQs, those handlers are executed. Okay, and this is happening a lot in a working system. Okay. So this is the second type of unusual flow in my system. And let us go to the third one, which is kernel housekeeping. So kernel sometimes needs to intervene in the process for some basic operations like collecting statistics, usage information, or adjusting timers, some timely events, freeing up memory, and so on. So we have this housekeeping task kernel has to do. And most important one is the scheduler, so which decides context switch to context switch or not to context switch. İşte bütün mesele bu. Okay, so the scheduler also makes this decision depending on type of scheduler you have. Okay, so this is the third one. And we need a mechanism for that. CPU belongs to P1. P1 is happily executed, doesn't have any system call to be executed soon. So how I am going to intervene it? What is the mechanism? Anyone? It is a timer interrupt. And I didn't mention something different from the hardware interrupt. Timer interrupt is actually a hardware interrupt controlled by kernel, not controlled, but adjusted by kernel. And it is a timely event. It is hardware and it generates, for example, in a typical system, 1,000 times in a second. So 1,000 times in a second, it gives you this interrupt, so you can do this housekeeping tasks. So that we can intervene. The fourth mechanism is, again, you are happily executing, but you need to make I/O. Okay. So this is user processes P1, P2, and P3. And there is hardware here. And this process, can it do hardware operation? So basically, hardware operation is what? It is just putting some registers in some place and calling some I/O blah blah operation. Assume there is a hard disk and you written some assembler code in your program, and that assembler code executes I/O blah blah blah. In 336, probably you have done something like that, do I/O operation directly. Can you do that? Anyone did it? Yapabilir miyim? Assembler instruction, I/O assembler instruction var bir tane, çok güzel. Port numarasını buraya yazıyorum, 03318. Register'lara da koyuyorum. Yapabilir miyim? Can I do this hardware instruction? Can I execute that hardware instruction in my process? Why? Oh, so you need a system call, but why do you need that? Yes, you cannot have that privilege. You cannot give that much privilege. Making any I/O instruction by the user process means you can write any area in your hard disk. Okay. You can access any packet arriving at network or computer engineering department's email server. You have a user process. You can access all people's network packets. You can access everybody's hard disk areas directly. And worse than that, you can write them. So you can write in the middle of a file system, so you can corrupt it. So we have serious integrity and security issues here. So in order to make that impossible, we put a boundary here and not let arbitrary user processes directly access hardware. So we have this distinction. We have this user space and kernel, and CPU work in two modes. By the way, this might be more than 2. In some CPU design, you can come up with 5 layers of security. But in a typical CPU, there are 2 modes, user and the kernel mode. So in user modes, this is not about Linux root access. Even Linux root user cannot execute IO instruction directly. Okay, so, but it's a good question. Linux root can access directly an IO device. No, it cannot. But Linux root can install some kernel module that does this job for it. It's okay. So we make system call and host decides if our call is valid and give access accordingly. Yes. And actually, the function executing your operation is written by some kernel programmer. So it is kernel code. It is not your code. And this is the important thing. Your IO request is executed in terms of the kernel's rules. Give me those parameters, and for them, I am going to give you that. And it does all of the necessary checks. Can you access? It is a file, it's a valid file, and so on. If somehow a piece of instruction sweeps into the hardware interrupt handler, can it reach the IO directly from there? Hardware interrupt handler, it is something you can reach very hard, so you cannot do that. If you don't do some sort of system call overflow, something like that, you cannot execute kernel mode operations. So there are security vulnerabilities that allows user processes to overflow kernel stack somehow so that they can inject some code. But other than that, it is not possible. Not interrupt handler, no, not system call, and so on. The user space is very limited. So you cannot execute IO. You cannot change memory mapping, and you cannot access kernel area or any other memory area than process memory. Okay. So it is restricted mode. In the kernel mode, you can do all of those. You can change memory, you can access, by change memory, I mean memory mapping. You can access kernel memory. You can access any physical page of memory, and you can do all of the IO operations. You can manipulate interrupt service routines and so on. Full control. Fourth one is system call. Spoiler vermek istemedim, o yüzden yazdım. Okay. So this mechanism is actually a mechanism which we call, so actually we have hardware interrupts turning out into some interrupt service routine, and system calls are software interrupts that call system call handler, which is actually the same mechanism. So in, for example, Intel 32, we have an interrupt vector, and in that vector we have interrupt number to function mapping, so that if 0 interrupt is executed, this function is 0 interrupt is triggered, this function is executed, and so on. We have such a vector of function pointers. And in Intel 32, there's 0x80, which is actually 128, is reserved for this system call handler. Sorry. This is a system call handler. So basically, they use same mechanism, but triggering is different. There is no wire for this type of interrupt. It is triggered through either syscall instruction or trap instruction. So it's in 64, it is syscall. In 32 bits, it is trap instruction. And those instructions will make a function call in the kernel space through this indirect processing, okay? So user process executes trap or syscall, and it triggers interrupt. And guess what? All ISR works in kernel mode. Software triggered, hardware triggered. They let your CPU go into kernel modes with rule of kernel functions. So these are adjusted by kernel. So kernel functions execute as a result. Okay. So these are our 4 mechanisms. And today I'm going to show you a couple of mechanisms and how they work. Any questions so far? System call handler is like a kernel function, and instead of triggering from hardware, it should be triggered from software. So what I do is I just register one handler here in interrupt vector as a function, and when I call this instructions in the user space, program, it will trigger this interrupt. So the kernel code is going to be executed. I'm going to show you these system calls. Okay. Actually, this is not a bad time, so I can directly show it when it is time. So basically, there is one system call handler. This is actually software triggered interrupt. Okay, CPU generates it to trigger itself, so that it will put itself into this kernel mode. From user mode, you execute an instruction. It is going to generate an interrupt in this table, very specific interrupt, and it will put you in kernel mode. So this syscall handler is something like that. Sorry. Of course, it is probably in assembler. But this is my register EAX. If it is 0, call read. Okay. Case 1, call write. Case 2, blah, blah. Okay, so it is something like this. Based on the some value of a register, it will take the corresponding action. And I'm just going to show you the evidence for that. Okay, so this is, I have one silly code, which is t.c, and I'm going to show you the system calls. If you like to see the system calls in such a code, you can install this strace in Linux. It is going to tell you which system calls your program does. Let me execute it again. So after those system calls, these are for loading code. It does alarm system call, then nano sleep system calls, and it goes like that. Now I'm going to show you how this is possible. In order to do that, I'm going to compile this t.c static so that I'm going to get rid of this. All of the libraries include everything in such a single binary. So T will be a static linked library. That means everything is in this binary. I don't need libc, etc. to execute. Now I am going to show you the assembler dump of this code. So this is my first system call. I'm not sure EAX value for this one. This one, it is 9E, okay, 9E, remember that. For this one, EAX value, I cannot get it, but 27, EAX is 27. 0xBA, 0xEA, and so on. So as you can see, 0xCA. So these are all system calls that my binary is using. So if you look into it, this is the user mode process executing these instructions. And when it executes this one, what happens? A software interrupt, software triggered interrupt is generated. And it will be handled by a system call handler, and it is going to look into a table in our system. Hiç Linux source'u görmüş müydünüz? If you didn't, this will be your first time. So I'm going to find it somewhere. So this is the place. This is the table. This table is compiled into some assembler code, and that assembler code is going to do what we need. So this is our table. 0 is read, 1 is write, 2 is open, and so on. Okay. So for example, 0xBA, 0xCA, for example, what is that? Well, CA, 202. That's futex. I don't know. That is a futex code. So I have seen EA somewhere, which is this one, and so on. As you can see, we have these system calls triggered this way, and they are actually handled in some other place. So after this table, they are so in this code, at least we are going to get our read implementation. It is read implementation calls, this one, and this is kernel code. So this is how you go from user code into kernel code. User space code executes syscall instruction. After a sequence of events, the kernel calls this function, and whatever this function returns is going to return to the user space program. Okay. Okay, so this is how it really is. in the working operating system. Thanks, we have a open source operating system, and we can see that. So this is the system call mechanism. I also have a picture with the system calls. Okay, so this is the same context switch picture with system calls. As you can see, these are the sleeps of P2 and P1. So this is an interesting system call. So when you start, actually the system call is triggered somewhere earlier here, I believe. So this is not precise, but the idea is P2 sleeps and wakes up here, and between them it is sleeping, not runnable. And same here, but the others only execute write and so on. Okay. So this is a short write invoked by the P1. Okay. So these are the system calls and how they work. So these mechanisms are, in summary, there's examples of exceptional flow. Any questions so far? Okay, so now I'm going to mention about context switch so that we can have actually in the list you will see like 300 something. We have IPC, inter-process communication, networking, system calls. We have system calls for probing the operating system, get process ID, set process ID, and so on. Probing the environment variables, what is my current working directory, and so on. Changing some of the process states, sending signal to other process like kill, setting a single handler, and so on. So there are plenty of system calls. I/O is an important subset of that. Thank you. You're welcome. So now let me just talk about context switch. So the context switch can occur in two different ways. One is, we can call it volunteer, and the other one is actually through this, what we call preemption. For this one, we usually have this timer interrupt intervening the process execution. So if you have a number crunching, this will happen. Timer interrupt will intervene. You executed a lot, so let's other processes can use CPU as well. So it is context switch to another process. The second one is volunteer. So the volunteer means through some system call like sleep or read, or there is a special system call called yield. Sleep means I am not going to use CPU anymore. I am going to sleep for a while, and after the sleep period is over, wake me up. So I give CPU voluntarily. In the read, if you are reading a slow device, most probably that read will take some time. So during that time, some other process can use the CPU. So operating system takes the CPU, puts the process into special state called sleeping state, and gives CPU to someone else. Yield means I am not going to sleep, but give my place to next guy. So this is something like that. You do it for kindness or when you are waiting for something, etc. Okay. The idea is, for example, there is a lock you like to get. You are pulling that lock, and between the pulls, you don't use CPU. You pull it, yield, pull it, yield, and so on. We are going to talk about that later. Okay, so these are those mechanisms, and this is the time interval. But whatever happens, actually we have this figure. Our CPU will belong to P1. Some kernel code executes through some mechanism, time interrupt or system call. And when this kernel code returns, magically, now P2 is executing. And this is what we call a context switch. And this is not a magic, of course. This is through changing the CPU context. And this comes with a question. What is the CPU context? So assume this scenario. You froze your CPU, take it out, or you save your CPU context, take CPU out, install a new CPU. What you need to store in that new CPU? Memory is some other place, and forget about the cache. Okay. What do you store in this new CPU? The CPU context mostly consists of these registers, and there are actually three registers that are very important. One is about this virtual memory register. I'm leaving that for following chapters. What two important registers you have? RSP, RBP. Okay, they are base pointer and stack pointer. I can consider them as stack pointer shortly. What else? Program counter. Again, instruction pointer or program counter. So those two gives you most important thing about your CPU. So what we need to do is, when in this code, I need to save a register set of P1 in main memory, and I have a different register set in my main memory, and recover this set. Okay, so that when I go into kernel mode, my instruction pointer is some P1 state and my stack pointer is in some P1 state. When I say that, when I restore P2, IP will contain this P2, and in this state, when I call return or return from interrupt, actually it is red eye, it is going to return to what previously saved context. So P1 calls, or kernel makes P1 call itself, and when kernel returns, instead of returning to P1, it is going to return P2. Why? I manipulated those registers. So this is how context switch occurs. However, it is expensive. It is expensive because this register context is not small. This is not a single byte. It is actually a couple of words and so on. It's like tens of words you need to save in main memory and retrieve back. But other than that, why it is expensive? Why context switch is expensive? Memory operation. Actually, you don't do much of memory operation. Assume you have 20 registers, you move 20 bytes or 20 words. Is it too much? Context switch cost is much more larger than this 10 bytes or 100 bytes. Because it is something like that. The process one is executing for, let us say, 10 milliseconds. And after 10 milliseconds, context switch, another 10 milliseconds. So in 10 milliseconds, how much instructions can CPU do? Like millions of instructions. And we are talking about 10 register move. So those 10 register move is not too significant if you compare it with 10 million. But yes, there is an answer from Onur Özkan, plus cached. So cache is the keyword here. Why cache is important? Because when I go here during this process, during this process, I have to invalidate cache. Actually, not this point, but this point. Okay. Why I have to do that? Why do I have to invalidate the cache? Especially address translation cache. We are going to talk about that later. Neden? One has some integer value at some location. And when P2 probe exactly same location, it should fail. It should get segmentation fault. For example, this one is getting some double value stored in that location. P2 is storing an integer in that area. And if that value is coming from cache, it is going to get invalid value. Probably P2 should get some segmentation fault, but it is not getting a segmentation fault because it is in the cache. And also address translation is completely different. And this will end up in integrity problems. And more importantly, it will have some security problems. So my process context switch by your process. So for example, my password in the memory will be visible to you. Okay. So this cache invalidation will end up in users getting each other's information. And there are some CPU bugs related to them. If you remember Meltdown, etc. 2 years ago, I believe, Intel processor. Even though operating system invalidates cache because of some CPU bug, it was not possible. So there were some side channel attacks repeatedly probing cache, and they will end up in getting the bytes. So this problem ends up in this cache invalidation. And that means when P2 wakes up, it is going to wake up with empty cache. So all instructions following that is going to get, main memory, so that following instructions will be slow. So following group of instructions will be slow until cache is sufficiently cache has sufficient entries to speed up the process. That's why the context switch is expensive. Okay. So we are out of time. So I'm going to stop now. Do you have any question? Actually, memory is the same, but cache is invalid. So main memory remains. So there is another register setting up the memory mapping PG3, something like that, and that will set up the main memory. Main memory is over there. However, cache is invalid, so everything has to go this slow path. Hocam, why do we have to delete the whole cache? Can't we just pretend like it's empty? How we are going to pretend that? So actually, The cache mechanism works as you just simply access memory. You don't have a special instruction to, I'm going to invalidate this byte only. You don't do that. You just read the memory and write the memory. That's it. But actually I talk, hocam bir açık vardı internet işlemcilerinde. Actually I talk about this meltdown and so on. Actually, this is what I was talking about. If you like, you can read about that. The cost of that bug is the kernels have to execute instructions to invalidate multiple cache at the time. So it's like multiply erasing cache, something like that. They recover this way. So we advanced so far, we had to go at the back, kind of makes me sad. I'm not sure about what you mean, but actually do not be frustrated because of what I have shown you. You don't have to know the tricks I am using. I'm just using too much material and visual aid just to give you an idea. You don't have to use those commands. You don't have to know where system call table is. Okay. Because of why context switching is expensive again. Because we need to invalidate cache. Did you follow that? We need to invalidate cache. And because of invalidation, since we invalidate the after context switch, the process is like a newborn baby. It doesn't have all of the memory operations coming from main memory, and they are slow. Main memory is slow. The idea of having a cache is it is fast, and you don't have that for first instructions until your cache has the area. Invalidating, I don't know how you invalidate cache in Intel. I'm not that expert in this assembler and organization, but there are instructions for invalidating cache. So you say invalidate this level cache, this level cache, this level cache. You call those instructions PU and main memory. So we have up to 3 levels of caches. So they invalidate only current core cache. But the idea is each core behaves independently. So each core has a kernel. You can assume like there are 4 kernels in the system if there are 4 cores. And each core, each kernel is invalidating its cache only, not the others. So it works this way. And installing their own hardware address translation. If you're asking about 2 cores in the same CPU and invalidating the CPU cache, I need to think about that. No, they do not. Actually, in cache, I mean address translation cache. Address translation cache is different than the actual cache. The actual physical memory cache is about physical memory, and there is no security problem here because accessing physical memory is controlled by the operating system. But address translation is process specific, and we invalidate this address translation cache. And it is in the core, I believe. Okay. Invalidate is is there a difference between invalidation and deletion? Actually, deletion is one by one deletion. Invalidation is completely trashing it. So we need to invalidate so that P2 doesn't access P1's cache memory. Yes, exactly. We invalidate cache that P1 resides in. Okay. No, the processes do not invalidate each other's cache. In their shared cache scenario, no, they don't actually. Okay. And now I'm not sure about the address translation cache, if it is repeated in level 2 and so on. I'm not sure about it. I need to check that out. I can come up with a better answer if I make a small research. Any question? Are there any CPUs out there to hold 2 caches at the same time for different processes, like one for kernel, one for resources? Yes, Intel processors are like that. I believe they have 2 different modes in Intel. I'm not sure. As I said, I'm not this computer architecture guy. I'm not following all these Intel architecture details and so on. But there is an idea. There are. I'm not sure how it is on the market, but in the cache you can do this. Instead of having this memory address value pair storing that, I can store this memory area process ID value. Okay, so in the cache, the lookup index contains process ID, so that I don't need to invalidate cache anymore, because process 1 is going to give process 1's ID, and it is only going to access process 1's entries. That means multiple processes are sharing the same cache. This is possible in the architecture. But there is too much operating system intervention in the cache. So instead of implementing pure hardware, it requires operating system putting this process ID in some register and so on. P2 never touched the invalidated cache, or does it treat it as empty and overrides it? The processes do not do anything. Processes just simply read and write the memory areas. But during that, the hardware is going to see that, oh, cache is empty, I should look at, or there is a cache miss, it is called cache miss. So I should look up the main memory. Cache miss, main memory, cache miss, memory. And the next instruction, luckily, okay, just 3 instructions ago, I accessed that. It will go like this, okay? Any other question? Software interrupt sinyaller için kullanıyoruz. Hani kille gönderdiğimiz sinyaller için software interrupt sözcüğünü kullanıyoruz. Ama onlar sinyal tabii, yani software interrupt değil. Hardware level'da oluyor. İşte tek istisna bugün anlattığım sistem kollar. Onlar software triggered interrupt. Any other question? Then thank you very much. I will see you next week. You can ask all of your questions into Cove discourse page. Do not hesitate if it is a simple question or not. All course content or